Yeah, there's a clock there and back there as well. Some water. Okay. Good afternoon and welcome everybody to today's press conference where we will unveil the results achieved by the Global Scientific Consortium Event Horizon Telescope, which aims to capture the first image of a black hole. A very warm welcome to all of you, especially those who have traveled from across Europe to be here today. We have very little time before the actual announcement goes live across the globe in 6 simultaneous press conferences, so I will break with protocol a little and hand the floor directly to European Research Commissioner Carlos Moedas, and then we will turn to the 5 leading scientists here on stage with us involved in the discovery. Commissioner?
Thank you very much. Let me put the timer. Thank you so much, and it's a great honor to be here today. We're really about to announce a huge breakthrough for humanity. We are about to take a picture of something that one man alone, dreamt, imagined 100 years ago in 1915, Albert Einstein. Imagine that. This idea that a very big weight transforms geometry, that when the mass is too heavy, you make a hole, a mysterious hole, where nothing can get out of it, where all is absorbed. Michael Kramer here from the ERC said, the history of science will be divided into the time before the image and the time after the image. And you know, for my generation, it's all about the imagination of something that was in between science and fiction. At the age of 9, I went with my father to watch the movie Black Hole. And I remember coming home and for the first time in my life, 9 years old, thinking about what's the meaning of life? What am I doing here? Is there any parallel universe? That's what really got me excited. And probably the question that we have to ask to us, to everyone here that really loves science, is to think about, what about in 100 years? Einstein was there 100 years ago, but in 100 years, what have we and what will be the discoveries? The things that we'll discover from these knowledge. You know, I see Robert de Graaf there that wrote a great book about the usefulness of useless knowledge. And Einstein could not imagine, he could not imagine what he discovered. He cannot imagine that one day, because he created and discovered the antimatter, that would create the PET scan that will save lives all over the world. So I'm really proud. I'm proud of science. I'm proud of science because science today is giving a lesson to politicians. It's showing that today to take a picture of something that one man dreamt 100 years ago, you need people from 40 different countries. You need people from all over the world, that at the same time that you're sitting here, there's 6 press conferences in Washington, in Tokyo, in Taipei, in Shanghai, and in Santiago de Chile. And I'm proud of Europe. I'm proud of Europe because we have invested so much in this project. We have put all together more than 44 million euros because we can be proud that Europe has a winning formula. And that winning formula is simple. We believe deeply in the freedom of science. We believe that scientists are the ones to make the choices. that the choices of science are not done by politicians. We believe somehow in the intuition of science. Stephen Hawking once said something that I would like to finish these words today with you, with this excitement of us. He said, "It is said that facts are sometimes stranger than fiction, and nowhere this is more true than in the case of black holes. Black holes are stranger than anything dreamed up by science fiction writers, but they are firmly matters of science fact." So, ladies and gentlemen, I think that I've not been this excited since when I came in 2014. If there's a big moment for all of us, it is today. And so this big moment is shared with so many in the public, so many today here, and I want to invite all the team. And for that, Professor Heino Falcke is here, so he will come immediately to my place and tell you, and we will join all of us here in the room, we will join him unveiling the image. So Professor, please come and I'll go.
I still have to, thank you. Now I have to fill the time actually until we're allowed to actually, start the unveiling sequence.
Introduce yourself and your team.
I thought I'd use the time to introduce our team here that's here today. On stage, we have Monika Mościbrodzka from the Radboud University, working on theory and imaging of black holes. Luciano Rezzolla from the Goethe University in Frankfurt. We have Eduardo Ros from the Max-Planck-Institut for Radioastronomie. And we have Anton Zensus, the director of the Max-Planck-Institut for Radioastronomy in Bonn, and also chair of the board of the Event Horizon Telescope. And we have, a lot of team members here in the front row. Michael Kramer was already mentioned, our co-PI. You have Remo Tilanos, the project manager of the Event Horizon Telescope. I'm glad you're here with us today. Colin Lonsdale, who is the co-chair of the Event Horizon Telescope project. Now we have to start with the session. We are looking into space, towards a galaxy, a giant galaxy 500 billion light years away from us. Sorry, 500 billion kilometers away from us. Very big galaxy which was suspected to host a supermassive black hole in the very center. 101 years ago, someone discovered a streak of light, which is plasma shooting out of the center of the Milky Way, marking the supermassive black hole. I never believed that this black hole was as big as people said, until we saw that. This is the nucleus of the galaxy M87, and this is the first ever image of a black hole. Das ist das erste Bild eines schwarzen Lochs.
This is the first image of a black hole.
C'est la première image d'un trou noir. What you are seeing here is the result of many people working together. You have probably seen many images of black holes before, but they were all simulations or animations. And this is so precious to all of us because this one is finally real. What you're looking at actually looks like a ring of fire. And it's actually created by the force of gravity, by the deformation of space-time, where light actually goes around a black hole, almost in a circle. And that creates that circle that we see here. It has a diameter of, I forgot the number actually. 100 billion kilometers. Now I got it right. It has 100 billion kilometers. But actually, at the distance, at the huge distance of M87, it actually will appear as a mustard seed in Washington, D.C., as seen here from Brussels. The size of the ring is actually determined by the mass of the black hole and very independent of all the parameters of the black hole or the modeling. And so we can derive from that size directly what the mass is. And it's 6.5 billion times the mass of the sun. That is an enormous black hole that we see there. We see also more in there. We see this dark region in the middle. I've always been asked by my colleagues, or told by my colleagues, you cannot see a black hole, can you? And I think they're right. You cannot see a black hole, but you can actually see its shadow. And that's when the light actually disappears behind the event horizon, creating that dark region, that dark shadow we see there. And this is amazing if you think about it, where if you know the story behind that image, we're looking at a region that we've never looked at before, a region we cannot really imagine being there. It feels like really looking at the gates of hell, at the end of space and time. The event horizon, the point of no return. That is awe-inspiring to me at least, but it's also important for physics. I think my colleague Luciano Rezzolla will now continue and explain to us why this is so important.
Questa è la prima immagine di un buco nero. So black holes are part of our daily knowledge. In fact, even a child knows what a black hole is. And the best definition I've received actually comes from a child who simply said, well, it's just a hole you cannot fill. So they're very simple, but they're actually extremely problematic in physics, and because of the properties they have. The first property is that at their center, in a single point, we think the laws of physics break down. We call this point a singularity. Another property is that this singularity is covered by a surface, a mathematical surface, which is called the event horizon. Gravity is so strong on this surface that nothing, not even light, can leave it. And this surface separates the interior from the exterior, and nothing from the interior can leave and be transmitted to the exterior. And for a scientist, this is a drama, because scientists want to know everything about every corner of the universe. So having a region where you say you cannot experiment there, or you can experiment there, but you cannot tell the results of the experiment, is extremely frustrating and puzzling. And the same puzzling thought was shared by Einstein. So how do you get to terms? You come to terms with this idea. Well, the first thing you want to do is convince yourself that black holes exist, and in particular an event horizon exists. And the image we have produced does exactly that. So you may wonder, how do you know it is a black hole? And that is because it matches extremely well with the prediction that we can do from theory. And this is shown in this picture over here. So on the left, there is the observed image. On the right, there is a theoretical prediction. And as you can see, the analogy is remarkable. As a matter of fact, we have carried out over these last 6 months the most extensive investigation of what happens to plasma, to matter, as it falls onto a black hole. We have used supercomputers and highly advanced numerical codes to calculate what happens. And what we've learned is that as matter falls onto the black hole, it will start rotating at speeds which are close to the speed of light, and will become hot and emit light, especially in the radio frequencies, which are the ones that our telescopes can capture. But these simulations are not sufficient. If you want to know what a black hole looks like as an image, you need to take into account that light doesn't move on straight line near a black hole. Just contrary to this room, light can come from all sorts of places. And so light can be bent, can be lensed. And so the image that you obtain by looking at a black hole can be very counterintuitive. And we have carried out a very extensive investigation. We built tens of thousands of synthetic images which cover all the possibilities that we think are realistic conditions under which a black hole is formed. And this is how we have come to conclude that this is a black hole, as predicted by Einstein. Now, you may ask, what is the meaning of this discovery? For many of us, it has different meanings, but there is one meaning that we all share and is very precious to us. We have transformed a mathematical concept, that of the event horizon, something that I normally write on a blackboard when I lecture on this, into a physical object, something that we can test and we can measure and we can observe repeatedly. And you may think this is a minor thing. Actually, this is a fundamental first step in any scientific progress. It's a scientific method. Be able to make an experiment and deduce from this what are the, how does nature work? And now I'll leave the word to my colleague Eduardo Ros to explain how this beautiful experiment was first carried out.
So, astronomy is not something that you do just from your desk. In many cases, you have to embark in an expedition. And 2 years ago, a large team of astronomers embarked in expeditions to the most remote places on Earth, in places where the atmosphere is thin and dry, because we need to observe at a wavelength where the atmosphere is important. The important thing of that is, in these locations are also facilities, as you see. They are like Iran 30-meter telescope or ALMA or APEX with European technology. And in these telescopes, the team of astronomers went there, prepared with one eye into the weather forecast, checking up all the systems of the telescopes, checking that everything works, and waiting for the go command when the weather was good in all the sites around the Earth. One of the tricks you need to make such an image of a black hole is to get a telescope as big as the Earth. And to get that, the small pieces of this telescope are parabolic antennas, which you can see the locations in the picture there. These teams were observing that. We had a fantastic good luck because we get good weather all across the globe at the locations of the telescopes. These data were stored in disks because you don't have optical fibers there. You have to fill boxes of hard disks, pack them into an airplane, in some cases waiting for several months, like in the South Pole, until the winter over is gone, because it was night in April 2017. You wait them, and these data are sent to processing centers where they are played back as they were recorded and synchronized with atomic clocks. These places are like in the Haystack Observatory in Massachusetts in the US, or in Bonn, Max-Planck-Institut. They are the so-called correlators. Data are played back, they are evaluated, and then they are given to a further team who checks this data. Every telescope is different. You need to correct for the characteristics of each telescope, put all that together so that you get a telescope as large as the Earth. And this process needed also several months of hard work, assessment, iterations, until people were sure, okay, this is the data that now we can begin to image. We can extract the information from this precious data, which occupied 6 cubic meters of disk, as I said, to get something like the image you have just seen now. And to know how you extract this information and you get from that, my colleague Monika Mościbrodzka will show us.
You may wonder how this image was made in the first place. Event Horizon Telescope data is like incomplete puzzle set. We actually only see pieces of the real true image. And then we have to fill in these gaps of these missing pieces to construct the physically possible image that is actually matching our data. This is actually a very difficult process. Therefore, the imaging process has been split into several phases. At first, at the very beginning, we were working on this imaging completely alone, each of us. This was a remarkable, almost life-changing experience to see an image of a black hole shadow popping out on the screens of our ordinary laptops. Next, we formed independent teams that work completely independent from each other to repeat the imaging process. This was a very necessary, important step because we wanted to get rid of the human bias as much as possible. And in the last phase, which took the longest time, the imaging was done very, very carefully via very careful scientific analysis. So what have we learned from the images, and not just from the images, also from the data that are lying underneath this image? So first of all, we have observed this source for 4 days. Over the 4 days, the ring is there. The image looks almost exactly the same. We have also measured the size of this ring. Over 4 days, the size is always the same. It doesn't change. We have also measured the contrast between the ring itself and the central darkness. And the contrast is as large as it is expected for the black hole shadow. But there's one more very peculiar thing about this ring. It's not really a full ring. It actually is much brighter at the bottom side. Why is that? Our models told us immediately that this kind of structure can be only formed if something in the source is rotating. What is rotating? It could be the black hole, but also the matter around it, or both can be rotating. At the moment, the images are not yet sharp enough to actually estimate or calculate the exact speed of this rotation. But these images give us a sense of the direction of the rotation, which is clockwise in the sky. So to summarize, our images, our data tell us that we are looking at the shadow of the black hole, which has been predicted by all the models of the black holes that we have developed over the last few decades. And now Anton Zensus will share some final remarks on the current state and the future of the Event Horizon Telescope. Thank you.
So my job now is to put it all together for you. The Event Horizon Telescope is a very ambitious project, but one with a very clear goal. We want to image, for the first time, the central black holes in the galaxy M87 and in the Milky Way. Today, now, 6 papers are appearing in the Astrophysical Journal Letters, a special edition, that show the image and all the discussion that is needed to convince our scientific colleagues. And in a few days, the data from our observations will be made public so that scientists anywhere in the world can verify our results. So how have we made this happen? We had to assemble a fleet, a capable fleet of the best and most sensitive millimeter wave radio telescopes in the world, combined through supercomputers to form one large radio telescope. We had to organize a team that now numbers to more than 200 scientists from many institutions around the world. This is a truly global collaboration. We cannot name all the people that are participating in this, but representative for all of them, I want to recognize Colin Lonsdale, Director of Haystack Observatory, and together with me, co-chair of the EHT Collaboration Board. He represents, together with our other friends here, the global partnership that we have, all the people that now are listening elsewhere that work together in this project. The preparation for these observations took a long time. I've spoken this morning to somebody who started 40 years ago building sub-millimeter telescopes. And so you can say several decades of preparation went into what in 2017 was for the team a very, very difficult, a complicated experiment to perform. This experiment was successful. This story is not a story of one hero. Instead, there are many heroes to this story. I'm proud to work with these people, and we salute their achievement. A number of them are here in the room today, ready to meet you later. So in Europe, how were we able to play a leading role in this endeavor? Foremost, it is through combining forces. We've brought together astronomers, observers, theoreticians, and facilities Together, we in fact were able to make a much better result than we would have been able to do individually. Of course, in Europe, we have direct access to some of the most powerful millimeter wave radio telescopes. The Institut Radioastronomie Millimétrique ERAM's 30-meter telescope was a crucial element in the north. ALMA, the Atacama Large Millimeter Array, where the European Southern Observatory is a key partner, was absolutely a game changer. It enabled us to get the sensitivity and the resolving power to make these images happen. Scientists in Europe for decades have collected the capabilities, have developed methods, have acquired the excellent skills that were needed to participate in the scientific process in this project in all places. And last, the technical development capability that we have to build instrumentation, state-of-the-art instrumentation that we need, is second to none here in Europe. Lastly, the public funds, the taxpayer money that was spent on our basic research here, both from national resources, but also from the European Union, from the European Research Council and from RadioNet, was crucial in making this excellence happen. We appreciate that very much, and we hope we can come back. So where are we going from here? M87 in the bag. We're confident that very soon we'll complete the analysis of Sagittarius A star. We will go back to observe, and so please stay tuned. We'll come back. We are already underway improving the array. Foremost, ERAM's expanded NOEMA array that they will soon finish will again be a game changer for our trade. ALMA will offer us improved capabilities. And the Greenland telescope and perhaps the African Millimeter Telescope project will make critical contributions to improving the quality of the EHT. With all of this, we're well placed to go into the next step of this journey. I think that we will be able to confirm a lot of the science that we're expecting. But much more important, we will be able, with this machine, to make discoveries of the unexpected. And that's the most fascinating in science. I personally like to say that I will think of a time before and after I saw for the first time this image. You mentioned this also. Today, I believe for all of us, marks the beginning of the day after for all of us. Thank you very much for your support, and thank you for your interest in our science. Now we will be ready to take your questions. Thank you.
Thank you much for these presentations, and I dare say our press room will always be open for such extraordinary announcements. Now we can turn to your media questions. Let me point out that we've published abundant not only press material and words, but more importantly audiovisual material on the Commission website. May I please ask you to introduce yourselves by name and media, starting in the middle?
Thank you very much. My name is Nicholas Wallace. I'm Policy Editor at Science Business. My question is for Commissioner Moedas. You said that this is the most excited you've been since you took office in 2014. My question is, do you expect any more excitement before your term ends? And if not, given that this was an international project that the Commission contributed to, what should be next for the EU and international collaboration in science? What do you think the next big thing should be for the next Commissioner? Thanks.
Thank you very much for the question. Yes, I think that this is really the pinnacle. I mean, I had exciting moments, exciting political moments, exciting when I was able to put forward to the College of Commissioners a proposal for 100 billion euros for the next science program. That really made my heart beat very much and made me more nervous about it at the time in a positive way. When then we went to the Parliament and the Council and we discussed, and a couple of weeks ago we achieved really something unique, is that we had that agreement with the countries and the parliament for the content of that program of the future. And so one of the things that is in that program answers your question, which is that is linked between the citizens and science, and how important is that. And so we want to define this idea of the missions, the mission-driven science, because we want European citizens to feel connected. And that connection that happened here today, it's a proof of that. You know, I've never seen this room so full, or if I've seen it, was not for positive reasons or for reasons of crisis, and not for positive things. And it's so refreshing to come here, to see so many people, to see people clap. I mean, it's very rare in a press room to have people clapping. And so I think that is a sign for politicians that you should look at science in Europe as really the engine of growth and the only way forward to be the center. And so in terms of international collaboration, and I've said it so many times, I really believe that this is all about the European program to be open to the world. I mean, we are discussing with countries like Canada, New Zealand, we're discussing around the world to have people that want to be part of the European program. Because the European program, as the history of Europe, is not about Europe, it's about getting people together. It's more than Europe, we are bigger than that, and that's what makes Europe be at the center stage. And so I think there's really for the next couple of years, that will be the mission. The mission is to get everybody on board in a place that is quite unique. You know, I mean, there's not a lot of places in the world where you have the funding that we have for fundamental science. We have Jean-Pierre Bourguignon sitting there with the European Research Council. I mean, that's quite unique, and so I'm proud of that. And yes, today is a really a proud moment.
Yes, Natalia?
Thanks for the question. My name is Natalia Drozdiak. I'm with Bloomberg. I was hoping that you could help us understand a bit what impact this discovery has on our understanding of conventional physics laws and how that's going to change now, especially with Albert Einstein's theory of relativity. Thank you.
So, you know, theory is eagerly waiting for confirmations. And Einstein's theory of relativity is the one that we know best and the one that has so far passed all the tests. And this is another very important test. This is the first ever image, and this gives us great confidence that relativity, as the one we understand in the strong field regime, where curvature is very, very strong, actually follows exactly what Einstein predicted.
If you look at the literature, there are a lot of ideas for alternatives of black holes, and this is something you finally can actually test. We only just starting to do this. We can now say it's not a wormhole, for example, but many other things we will test in the future, but it can be done now. Now it becomes experimental science. And we have gravitational waves, and we have pulsars, all testing gravity in an area, in a regime, which has been inaccessible before. And so I think this really transforms the study of gravity in a fundamental way. Really different methods, different scales.
Thank you. Gentleman here in the front. You can take a mic on your side, in the seat. Now.
I'm Davide Castelvecchi from Nature magazine. How many questions do I get?
Can we start with one and then we'll vary it a bit?
Okay. Can you tell us if you found any information about Sagittarius A star?
Okay. I was supposed to say that. We actually focused all our attention on M87 when we saw the very first results, because we knew this one's going to be awesome. The issue with Sagittarius A star is 1,000 times smaller, it's 1,000 times closer, so it has the same shadow size, but it's also 1,000 times faster. So if you want to take an image of that source is like take an image of a toddler which moves around for 8 hours and try to get a still image. While M87 is a big bear, 1,000 times slower, hibernating there, not moving much within these 8 hours. So that makes it much easier. We were just lucky that M87 was so large. It could have been much smaller. We didn't know that before. And so once we saw that, we focused everything on that one. So, we'll still take a little more time to work on Sagittarius Star.
We may come back to you later, time permitting. I think I saw some other show of hands. Yes, back there. Markus first, and then in front of you.
Markus Becker with Der Spiegel. I see that the black hole seem to behave nicely and follow the predictions, but maybe you can explain to us what kinds of new insights you have gained and how they form the basis for possible new research and new insights in the future. Thank you.
So far, our observation is actually exactly what we have expected. But I think there will be more possibilities in the future to investigate the behavior of this black hole. We basically would have to take movies, not just static images. Yeah. We also can learn something about the jet formation. This supermassive black hole is very famous for its huge kiloparsec scale jet. So now we know how this jet is actually coming out from the black hole. So this is a huge new insight of how relativistic jets are produced.
Thank you. Then we had a question right in front of Markus. There? Yeah? No? Okay, well, maybe while you continue thinking about questions or we come back to nature, we also have a number of people following us on social media and online, and they also had the opportunity to ask us questions, so I'll take a couple of those. Firstly, how can you take photos without light?
Well, radio is also light. The radio waves as light as the eye that enters into these detectors we have here, which are called eyes. We use the light, the waves that come from the remote black hole region in such a quite tricky way, because the same light that arrives to the Earth, the same wave comes to all the different telescopes, and we trap this front of light in our computers. We can then reproduce and play back that, but this is also the radio light, which is also the same light that comes into the mobile phones and all that. We are working in the electromagnetic spectrum. Then we can use this light to see the black holes too.
What we see in the image is actually light that is produced by plasma around the black hole. It's true that we cannot see the black hole. It's black, so you cannot see it. But we see its shadow that is being cast on this glowing plasma. So we are actually taking a picture of light.
One little detail, we think that the black hole is actually really engulfed in an optically thin, transparent, glowing fog of radio-emitting material. And so the fact that you see nothing in the center is actually quite significant.
Then we'll take another question, which I think is rather directed at Commissioner Moedas, which is how will the EU support astronomy, that we're now all very fascinated about, in the next EU research funding program?
I think first we support it in the name of our new program. You see, Event Horizon Europe. I never thought about that before, but I think it's a good one. I think that the way it's very important that Europe keeps on being the leader of fundamental science in the world. I mean, that's where we are at our best. And so when we approached on this proposal for the countries and for the parliament to go from 13 billion euros for the European Research Council to 17 billion euros of the European Research Council, that's exactly about fundamental science. And that's exactly to put this priority as a European priority. Because if we can differentiate there, I think that we can differentiate for the future of our children. Because what I love about fundamental science, and I think that's the question from the journalist over there, which was, but what do you take from here? What are the impact? And the things that we don't know, there's so many impacts that these will have in the future. I think that it's interesting to look at the people that are young now, the very young ones, and think the impact that they will see from this in 50 years, and the fact that we don't know. And that's something that is for the good of Europe and for the good of the world. So I think that if there's a place in the world that invests in fundamental science, it's us, and we should keep doing that for the future. So on the program Horizon Europe, we will keep investing very heavily on fundamental science.
Thank you. Of course, Anton?
From my perspective, and that is that it is very important to see that Europe is investing in the great brains. And at the same time, it's also very important to see that we have in Europe this technological and this edge with our facilities. And I will say that the support that we've had from the Union in actually making these facilities accessible to pan-European scientists has been very important. And even more important has been the seed funding that we have received so that the technology development can be done together at various institutions. And so it's the balance of investing in the individual talent, the brains, and investing into state-of-the-art infrastructures that really sets us apart.
Thank you. Let's come back to questions in the room. Yes.
Hello, Adi Nauwman from Astronomy Netherlands. I have a question about the accretion disk of black holes. All black holes seem to have an accretion disk. Did you try to have an image of that accretion disk too? And how do I see the accretion disk compared to this image? Is it outside of this horizon, or I don't know?
So, as you correctly said, these black holes are not in vacuum. They are surrounded by matter, and matter naturally folds and circles around it. Now, in this very image, the accretion disk is essentially as my hand. We're seeing it almost face on. And so it happens that matter that rotates in particularly in clockwise direction, will be pushing towards us. It's all of its emission, and this is why the bottom line is more bright than the top part, because it's what is called Doppler beamed. It's more intense because of a relativistic effect. So you can imagine that there is matter going around in a clockwise in a kind of accretion disk. The disk is not thin as we normally see in science fiction. It's a very thick accretion disk, and the simulation that you will find online will clarify this a bit better.
I would like to add here that it is okay to, this image can have different interpretation, and it is possible that we are actually, that this ring is actually the inner edge of the accretion disk.
Or the inner edge of the jet. That's where it starts. The problem that we have is that the light bending actually blends everything together. So when you look at low radio frequencies, you see the jet. As you go to high frequency, you get closer and closer to the event horizon. That's why I went to this high frequency, because that's where we actually start engulfing the entire black hole. That's where we can resolve the black hole, but that's where the innermost region is, and then everything gets blended together by light bending. So if you look again at the simulations, then you get a much better idea of what we think there is.
For the Spanish news agency Agencia F. Does the black hole actually has a name other than the black hole of the M87 galaxy?
It didn't have a name, and in analogy to the other source that we study, Sagittarius A star, we just used this short version and called it M87 star, which doesn't mean it's a star, but the star actually means it's a very exciting source. It's one of the most exciting sources in M87. So.
As an amusing note, the reason Hawaiian name which has been associated and proposed for this black hole, so we'll actually have a proper name besides just a number.
Thank you. It's a good idea for a contest, though. Yes, back here, down here. Push the button and wait until it turns red. Yeah.
Koen Wouters, VRT Belgian Television. Have you found something which was unexpected or contradicted Einstein's relativity theory?
Unfortunately, not. I think it was mind-blowing to see that in the first place. had it been completely different from our expectations, we would have had to puzzle for like 2 more years to really, see had we done something wrong. Of course, at some point, you hope to find something that you did not expect in your simulations. By now, everything seems to fit perfectly, actually amazingly perfect. And I should say, actually, Monika published, shockingly, she published a paper 2016. If you just convolve it to what we observe today, it's almost what we see now.
Thank you. Any further questions in the room? Yes.
Hello, Dr. Renzen, Deutschlandfunk. Can you really exclude any possible, maybe remotely possible alternative explanation? Or could it be, for instance, connected to the area where the jet is launched?
Actually, no, we cannot exclude. There are many alternatives to black holes, and there are many black holes in other alternative theories of gravity. What we are doing right now is excluding some of them. For instance, wormholes, as Heino has mentioned. We can exclude boson stars, which is also a very popular alternative. There are other alternatives which are more subtle and will require future observations. But what we see is consistent with Einstein's, and that's the simplest explanation. All of other explanation requires some more exotic explanation that would be difficult to explain with astrophysics, for instance, but are still allowed by the theory.
One little addition, we ran our simulations actually all kinds of physical scenarios. So we had actually disk-dominated, jet-dominated. Emission would come from all over the place, and it turned out it almost always looked the same because of the light bending. That is a dominating effect. So, we simulated all of that, and wherever it comes from, the GR wins and sort of makes that shadow. That was actually the predictions and seemed to work out very nicely.
Okay, we'll take another question from social media. Are there any other galaxies that we know of where we might be able to observe black holes?
Eduardo.
Yes, they are, and they are in our list. I mean, these galaxy and Sagittarius star are very strong. As long as we develop our telescopes to go to bigger collecting surfaces, which make us more sensitive to the photons coming from the universe, we will tick our list and check for the next ones.
The problem is if you want to resolve the black hole, you have to go to higher resolution, and you need a telescope larger than the Earth. And that you can only do from space. And so watch for some papers in the next couple of weeks or so, which will describe how you could do this.
Do we have any final questions? Yes, the gentleman back there. You have a microphone and
Julian Moore, just a European citizen, astonished by what you have achieved. My congratulations. I simply wanted to ask, you did some simulations to give you some expectation of what you would be looking for in your results. According to the parameters of your modeling, did it give you any insight into the other parameters of the black hole, such as its magnetic field or its angular momentum? Did it shed any light on the generation of the jets? Pun intended.
So, yes, thank you for your question, citizen. That's very, very important. Rotation of the black hole is very difficult quantity to measure. And because of this blending of the light coming either from the jet or the accretion disk, it's very difficult for us, and this is something we discussed in the papers, to measure exactly how rapidly the black hole is spinning. But we think it is spinning because otherwise it would not make sense in terms of the energetics of the jet. And so we think it's spinning. And actually, if you want to ask, well, what is the spinning direction? We think it's pointing away from us. That's our best guess at the moment. And learning about magnetic fields, that's something that we are working on. But right now, we don't have a conclusive answer yet. Again, these are much higher, much more difficult quantities to measure. And we hope with a future observation to nail down also this information.
I would like to add here that at the moment we have a sense of rotation. So this is something that I mentioned, that it is clockwise on the sky. So this is something that we are certain about.
I may add on the magnetic fields that these data have still treasures waiting for us. We have obtained the total intensity images, but we are working also in the polarized light, which is also in the data. And when we learn about the polarized light, we also learn about the magnetic fields. This is one of the next things in our to-do list.
Thank you all. We will be closing this press conference shortly. Before I invite Commissioner Moedas to formally and officially close the press conference, let me, of course, thank our speakers here and all of you for being here today. I would also like to thank our interpreters and technicians, because it's not every day that they have to translate such a scientific language and also put up all this show. Our scientists will actually be with us still afterwards, so if journalists belatedly think of any questions, they're welcome to approach them. And with that, Commissioner, the floor is yours for the closing remarks.
Just a word of thanks to everyone for this amazing moment, but a word of thanks for the courage, because, you know, it's not easy for the scientists to take the risk. I mean, we were taking a risk of being here today, and that is something that is important for Europe, that you take the risk to be here, you take the risk to be in this moment, and to show to people the importance of science. And more important to that is that you made us dream today, and an important moment. You know, we go through difficult times, a lot of crises, a lot of problems, and sometimes we need these moments. And this morning, when I was reading a speech from Stephen Hawking that he delivered in Chile quite long ago, I thought that I would finish with a quote from him that would inspire us to be hopeful about the future and will inspire the leaders and the prime ministers and the presidents that are here today in Brussels. He said the following: "Black holes ain't as black as they are painted. They're not eternal prisons as we thought. Things can get out of a black hole, both to the outside and possibly to another universe. So, if you feel you are in a black hole, don't give up. There is always a way out."
Thank you all. Let me also invite you to join us outside, for those who are physically present here today, for the exhibition that we have on the project. And with this, we conclude the press conference. Thank you.
Gracias.